Okay, so in this video, we're finally going to introduce the concept of eigenvalues. So just to give you an idea of what eigenvalues are, I'm going to talk about a matrix A that is defined as follows. So it's just going to be a 2 by 2 matrix. It's just going to be a 2 by 2 matrix. And let's say, for the sake of argument, that we were interested in finding the power of this matrix. So let's say we want to raise this to the power of 100. So you know by matrix multiplication that because you're essentially just multiplying this matrix by itself 100 times, you're going to get a 2 by 2 matrix. So 1, 2, 3, and 4. And those are not zeros, by the way. Those are just like general numbers that you're going to get. And obviously you will carry out the multiplication using the rules that we have described in previous videos, but obviously that will take you a very long time. And you might say, well, we can easily do this on a computer. We can just open our Octave and then just perform that in there without having to go through a lot of trouble. But the thing is, you see, the thing is that with this kind of matrix, we cannot just perform this, because what if we wanted this to the power of 1 million or something like that? So let's say 1 million. Computationally, this will take a long time, and at some point you're going to run out of resources to actually perform this numerical multiplication on a computer. So how can we actually go about performing such an operation without actually consuming all the resources that we have available in terms of hardware? Well, the answer to this is something called diagonalization. The answer to this is diagonalization, and the whole point behind this is that we're going to find a matrix D that is a diagonal matrix, and it's going to be related to this. So it's going to have two values, only values along the diagonal that are non-zero, or they can be zero, but in general you will have two different values. So if we have a 2 by 2 matrix, then the diagonal matrix corresponding to A will have only two values, and those will go along the main diagonal of that matrix. And this is what we call the eigenvalues. So eigenvalues. They're essentially two quantities that are calculated from this matrix that allow us to decompose it into a matrix that can be actually raised to some power, arbitrary power. And by the rules of operations with matrices that we have already learned, you would see that you can actually just raise each of these quantities to that power, or whatever power it is, really. Because when you perform this kind of operation on this, what you're going to get is you're always going to get a 2 by 2 matrix that has zero everywhere else and just values along the diagonal. So if you multiply, for example, this matrix twice, which is the same as squaring it, you're going to get lambda 1 squared and lambda 2 squared, because that's the property of diagonal matrices. When you multiply a diagonal matrix like this by another diagonal matrix, you're just going to be multiplying the corresponding elements here, because everything else is going to cancel out as a result of how you perform matrix multiplication. And this is a lot easier to computationally determine, because we know that this is just taking a single number at a time and just raising it to that really large power. So this is something that we can easily do in a computer. And this is not just complete. There's another thing that we need to calculate. So in general, we want to express the matrix A as follows. We want to express the matrix A as follows. So we're going to have another matrix P times the diagonal matrix, which is this one, and then times another matrix, which is the inverse of P. So if matrix D is a diagonal matrix containing the eigenvalues of A, then matrix P is going to be another squared 2 by 2 matrix in this case that is going to contain the eigenvectors of P, of A, sorry. So eigenvectors V1 and V2, which is the same as saying we're going to have V1, V1, 2. Just going to add a little, and then V2, 1, V2, 2. So essentially we're going to take these two column vectors called eigenvectors, and we're going to set them out in columns like this. So we're just going to place the values in there, take the inverse of that, and then perform the multiplication in this same manner. And what that And what this will allow us to do is, if we want to raise the matrix A to some power of n, then here we're going to have p d p minus 1 to the power of n. And because this is a diagonal matrix, what's going to end up happening is this is going to be carried on only onto this. So in the end, we can just raise d to the power of n, which is this operation that we just did here. And then the other two matrices are only going to be multiplied in the end. So once we calculate these values, we can plug them in here, and then the multiplication becomes just a multiplication of 3 matrices, which is a lot better than multiplying a million matrices. So this is the whole point of this concept behind eigenvalues and eigenvectors. And we'll see in later videos as well that these have some really interesting applications for solving systems of differential equations. And that's another really nice thing that comes out of these values. So now that I have pretty much just laid out what eigenvalues and eigenvectors are, I can actually start talking about how to calculate them. So let's say we have a matrix A, which is composed of a whole bunch of elements, A11, A21. Actually, the row number comes first, so that's 1, 2, A13, and so forth. And then we have a bunch of values here, AN1, and then we have a bunch of values here. And you can imagine that I'm just going to fill out this matrix. And by the way, in order to find eigenvalues and eigenvectors, as you would have guessed, we need square matrices. So this only works for square matrices. Alright, so we're going to do the following. To find the eigenvalues, what we're going to do is we're going to find the determinant of the following matrix, which is A minus lambda I, and lambda is going to be the values of our eigenvalues, and I is just the identity matrix. So we're going to set this equal to 0. So whatever comes out of this is going to be a polynomial of lambda, and then the roots of that, of polynomial, are going to be the values, the eigenvalues that we get. So we're going to have the following determinant of the matrix A. Actually, I should do it like this. So matrix A minus, remember the identity matrix is essentially just all ones along the main diagonal and zeros everywhere. So we're going to have lambda, 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 and so on, and then zeros everywhere else. And all of this equals to 0. And then obviously these lambda values are going to get subtracted from the main diagonal here. So in the end, when we perform the determinant, we're going to get a polynomial of lambda, and then the eigenvalues are going to be the roots of the polynomial of lambda that we get from this determinant. And remember that for any, we can find the roots of that, and sometimes we may have repeated roots. We may have something like lambda minus 1 squared, and then we would actually have an eigenvector for each of those, because remember we need to have equal number of eigenvectors as eigenvalues, and then we're going to construct our D matrix from that. And once we have found those roots and those eigenvalues, we can perform this next operation, which is for each eigenvalue, so I'm just going to denote it lambda n, we're going to have an eigenvector Vn such that it satisfies the following equation. So essentially we're going to grab the matrix again, we're going to subtract that particular eigenvalue from it, times the identity matrix, and then times the eigenvector. So this is just like, this is pretty much the same process as just solving a system of equations. So we're going to have some values here, A11 minus lambda, A22 minus lambda, A33 minus lambda, and then whatever other values we have of A. So that's going to be lambda n, because remember we're going to take one eigenvalue at a time and we're going to perform this operation times the value of this. So we're just going to denote a v1, v2, and so on and so forth equals to 0. And you know that this can just be treated as a 0 vector, so we just have a column vector of zeros. And then we're just going to set up an augmented matrix, as we have done in the past for row reduction. And using row reduction, we're actually going to try and derive expressions that will solve this particular system of equations by looking for pivot points or pivot elements in that matrix, and then deriving expressions that involve v1, v2, and so on. And then we can find the value of that eigenvector. And that's what we will do in the next few videos. So in the next video, I'm going to go through an actual numerical example, a simple example using a 2x2 matrix of how to find eigenvalues, and then we can apply that knowledge to find eigenvectors and diagonalization. So that's what we'll do in the next video.